A robot can pour liquid into a glass, throw a ball, saw wood, and do many other types of activities. It eventually learns how to perform these tasks by itself in unstructured environments, such as in industry or at home. A humanoid robot can see an object and can link the object with its movement. However, the robot has to learn with what force to grasp the object and what to do with it. This humanoid mannequin has the same temperature as the human body and can sweat as well. It is used to evaluate the thermal characteristics of protective clothing and is thus instrumental in the development of protective garments. The research program group Automation, Robotics, and Biocybernetics at the Josef Stefan Institute is the largest such group in the field of production technology in Slovenia. The founder of this group, Professor Jadran Lenarčič, embarked on a bold experiment to combine the fields of life science and technology.
This group combines researchers from many fields of robotics, biocybernetics, biomechanics, kinesiology. This enables to solve very complex problems in industrial robotics, industrial automation, in cognitive robotics and service robotics, as well as in environmental engineering.
Our international research group comprises of established scientists, postgraduate students, research engineers, and technicians that initially continued their leading-edge research in their own fields, but eventually combined forces to achieve research and development breakthroughs in several common areas of research. Initially, the common denominator in the group's R&D was the interaction of humans with automation, technology, and robots, as it relates to industrial manufacturing processes, biomedical engineering, and rehabilitation. Present research has now expanded this so to include human movement as well. Humanoid robots are being empowered with cognitive skills, enabling them to learn to assist humans in various tasks in extreme environmental conditions.
By maintaining a critical mass of excellent researchers and supporting multi- and interdisciplinary projects, we maintain a research program aimed at improving the quality of life, especially the elderly and infirm. We are able to efficiently utilize and combine the results of technological and scientific advances in humanoid robotics, biomedical engineering, and environmental life sciences in projects concerning the safe interaction of automation technology and robots with humans working in extreme environments. Our current vision of human-robot interaction during future expeditions to the Moon and Mars has enabled us to establish outstanding research partnerships with leading research groups worldwide. The results of this research will be directly applicable to target groups on Earth and will herald a new era of industrial robotics and automation in manufacturing technology.
Transfer of knowledge to industry is one of the main aspects of our work. At this moment, our research tasks are concentrated around automation procedures in the glass, shoe, and food industries.
Within automation, we are developing advanced robot control strategies for robots working in unstructured environments, for low-level reflexio control, and for robot cooperation.
We have developed new methods for robot motion synchronization and intuitive, supervised robot learning for rhythmic tasks. For kinematically redundant robots, we have proposed new control strategies for efficient control of robots performing prioritized tasks and for a smooth transition between tasks. These methods ensure safe robot operation also in the presence of humans in the workspace.
We have built a unique robot skier which is used for evaluation of control strategies in the laboratory and in the field.
One of the most straightforward methods to achieve human-like behavior of robots is to transfer the motion from a human to the robot.
We developed a novel paradigm to efficiently teach robots how to perform complex dynamic tasks both individually and in cooperation with a human partner. The approach utilizes human sensory motor learning ability, where the human tutor controls the robot to perform the desired task through a multimodal interface. During the tutoring, the robot simultaneously learns the action policy of the tutor and through time gains full autonomy. We demonstrated our approach by various robotic tasks. In the most recent experiment, we taught a robot how to perform a highly dynamic wood sawing task that requires precise coordination of the robot's motion and compliance according to the partner's actions. In the future, we will utilize the developed paradigm for the intelligent control of a special kind of robots that will be attached on the human body. These exoskeletal robots will provide mobility assistance for elderly and infirm people.
The goal of research in the area of humanoid and cognitive robotics is to develop robots that can operate in natural environments and in collaboration with people. This is only possible with robots that can continuously and autonomously acquire new sensory motor behaviors and higher level knowledge. Due to their similarity to humans, humanoid robots are especially suitable for operation in environments shared with people.
We contribute to the development of such robots by investigating new technologies for the perception of the external world and seamless learning with or without a human teachers. In the past few years, we developed new methods for the integration of sensing and motor control, new techniques for reinforcement learning and imitation learning, and new methods for autonomous learning, taking into account the forces arising when interacting with people or the environment. Our research is included in a number of large European projects in the area of cognitive systems and robotics.
We developed a new algorithm for the robot sensory motor learning based on statistical generalization. Using the demonstrated activity and based on previous experience, the robot improves its actions and saves this knowledge into a database.
Whenever the robot encounters a new situation, it searches for the solution in the knowledge database. If it can't find an appropriate solution, it tries to learn appropriate behavior from similar actions.
This kind of learning is much more effective than learning without using this experience. We have successfully applied our algorithms in tasks like pooling,